In this video, we're going to start with the assumption that we already know about angular momentum and the conservation of angular momentum. And we're going to derive a formula for the angular momentum of a point mass moving with some arbitrary velocity v. So we're not talking about a point mass moving in pure rotational motion here. Instead, in our picture, we see our point mass just moving along with some arbitrary constant translational velocity. And we've also labeled a reference rotation axis, and we're going to compute angular momentum with respect to that reference axis. So as this mass tracks along, it is going counterclockwise with respect to our reference axis. And we just imagine pointing at the mass with a position vector as it flies by. And that position vector is rotating counterclockwise, but it's not doing that at a constant rate. In addition, the distance from the rotation axis, in other words, the length of the position vector, is changing. But it's still going to turn out in the end that the angular momentum of this point mass is a constant. So before we get started, I want to establish why we even care about this. And the reason is that it will allow us to solve a certain class of collision problems where an initially moving point mass collides with another object, resulting in a final rotational velocity. So to give you a peek at the problem we're going to do at the end of this video, we have a wad of clay impacting a rod that's hinged at one end, and the result of that impact is a counterclockwise rotation about the hinge. And the basic approach to this kind of problem is angular momentum conservation, but first we need an expression for the angular momentum of a point mass moving with a translational velocity. So back to our derivation, we're going to start with the fact that the angular momentum of any body is given by I times omega, where I is the moment of inertia of that body and omega is the angular velocity. So the first thing we want to do is figure out the angular velocity of this point mass, and that depends only on its tangential component of velocity. So there's our tangential component of the velocity, and if we label the angle here between the position and velocity vectors, we see that our tangential velocity is given by v times the sine of theta, where theta is the angle between the position vector and the velocity vector. Now that tangential component is related to the angular velocity by v equals r omega. So the tangential speed is given by the distance to the rotation axis multiplied by the angular velocity in radians per second. And I'll post a link to the video where that was first derived. So now we can just solve for omega here, and we get v tangential over r, but then we replace v tangential with v sine theta. And there's our expression for the angular velocity of this point mass as it's tracking along with this constant translational velocity. So just a quick reminder before we write down the angular momentum of this thing, the moment of inertia of a point mass is given by mr squared. So we write down the angular momentum as I omega, and we replace I with mr squared for this point mass, and we replace omega with our expression v sine theta over r. So now one of the r's is going to cancel out. And we're left with this expression r times mv times the sine of theta. And the reason I wrote it in that order is just to recognize that mv, well, we have a name for that. That's the momentum of this particle. So we could just write this as r times p times sine theta, where p is the momentum, mv. Now we can formally include direction in this statement by framing it as a cross product. So we can write that the angular momentum vector is given by the position vector crossed into the momentum vector. And using a right-hand rule to understand the direction on this, we sweep our fingers of our right hand from the direction of r to the direction of p, and our thumb points out of the page. So our formal direction for the angular momentum in this picture is out of the page. But that really just means counterclockwise, which, by the way, is the same direction your fingers curl if you point your thumb out of the page. So I normally remember two different ways of writing the angular momentum for a point mass, and first and foremost is r cross p, but it's also good to remember a formula for the magnitude of the angular momentum, and I normally write that as mvr times the sine of theta, and again, that's just the magnitude of the angular momentum without including the formal direction of it. So one important point about the angular momentum of this isolated particle is that it doesn't change as the particle flies by. And we know this has to be true anyway, since angular momentum is conserved in the absence of an external torque. But it's instructive to look at the details here. So to illustrate, we show the mass moving between 2 points on its straight trajectory, and point number 1 is the point of closest approach to the rotation axis. And at that point, the position vector is perpendicular to the velocity or momentum vector. So then at some later time at point 2, r is going to be larger in this case, and the angle changes between the velocity vector and the position vector. So now instead of 90 degrees, we have some angle of theta in there. So we can compute the angular momentum at the point of the closest approach. And again, I'm just remembering mvr times the sine of theta, but theta is 90 degrees here. So we end up with mv times r min, where that's the closest approach distance to the rotation axis. So there's the angular momentum calculated at point number 1. And now we want to repeat this at point number 2. And so I quote the formula mvr times the sine of theta. But r times the sine of theta has a geometric interpretation, with r being the magnitude of the hypotenuse of this right triangle that we're looking at. R times sine theta is the magnitude of the opposite side to the angle theta, and that's just r min. So we end up with the same value for the angular momentum of this point mass, no matter where we do the calculation. And the main point is that it's often convenient to look at the angular momentum of our point mass at the point of closest approach. In other words, the point where the position vector and the velocity vector are perpendicular to each other. And that's exactly what we're going to do in our example. So getting into our example now, we have this overhead view of a heavy beam. It has a mass of 10 kilograms. And it's hinged at the bottom end here. It has a length of 1.5 meters, and we throw a big ball of clay at the end of it. And the ball of clay has a mass of 2.0 kilograms and a speed of 7.5 meters per second. So this ball of clay is going to smash into the end of the heavy beam, and this results in a rotation of the entire system and some final angular velocity that we're trying to compute in the problem. So the key prerequisite to using angular momentum conservation to solve this is having confidence that there's no external torque acting on the system. So we just have these two isolated objects. They end up with a collision between them. They exert torques on each other, but there's no torque acting from outside. So we're going to approach this with conservation of angular momentum, and we say L initial is equal to L final. And then to get the initial angular momentum of this clay ball, we're just going to imagine that the ball arrives at the point of closest approach, the point where the position and velocity vectors are perpendicular. And I'll go ahead and just quote it the way we wrote it down as mv times r min for the angular momentum of this ball. Again, that's always the same number until the collision happens, but it's particularly easy to compute at this one spot where the velocity and position vectors are perpendicular to each other. Okay, then to get our final angular momentum, I have these two objects that are stuck together and then they're experiencing this pure rotation. So I need to get the total moment of inertia of the combined masses. And this starts out with the moment of inertia of the beam itself. And we recall that that's given by 1/3 times ml squared when we rotate a rod about one of its ends. And I'll post a link to the video where that was derived. And then this is added to the moment of inertia of the point mass that's stuck to the very end of the beam. And we used a little m for that mass, and it has the same distance from the rotation axis as the length of the beam itself. So that's going to be a little m L squared. Okay, so there's the total moment of inertia of the combined objects, and then we multiply that by this unknown final angular velocity, and that's what we're trying to solve for. So we can go ahead and just solve for omega symbolically real quick. So that's mv times r min over 1/3 big M L squared plus little m L squared. And we have a couple things to clean up here. First off, r min, that's the point of closest approach to the rotation axis, is the same thing as L. So I can go ahead and cancel one factor of L out of this. And I'm also going to multiply the numerator and denominator by 3, just so I don't have a complex fraction. So I end up with 3mv. And then in my denominator, I have a big M times L plus 3 little m times L. And I'll just factor the L out of that, and I end up with L times big M plus 3 little m. So that's a nice way to write the symbolic solution, and now we can plug in our numbers, and I end up with 3 times a mass for the clay ball of 2.0 kilograms times its initial speed of 7.5 meters per second. And then we divide by the length of this beam, 1.5 meters, times the quantity big M, which is 10 kilograms for the mass of the beam, plus 3 little m, that's 3 times the 2 kilogram mass of the clay ball. And when I run the numbers on this to 3 significant digits, I get a final angular velocity of 1.88 radians per second. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left. or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.